Hello everyone, welcome back to our lecture series on internal forces in beams. I'm Chaminder and in this video I'm going to explain you how to draw the bending moment diagram, shear force diagram and axial force diagram for a given beam using an example. Okay, let's work out on this example and learn how to draw the bending moment diagram, shear force diagram and axial force diagram for the beam AB. As you already know, first thing we should do is to calculate the reaction forces for the analysis. To calculate the reaction forces, we should mark the possible reaction components at each support. Now in this beam you can see at point A it's a pin support which you can represent with two reaction force components, one vertical and one horizontal, and at B it's a roller support. So you can mark the vertical reaction component. Now you can see a uniformly distributed load of 40 kilonewtons per meter acting through A to D of the beam. As you know, we can represent this uniformly distributed load when we calculate in the reaction forces, or whenever we need to calculate the moments, that we can simplify this uniformly distributed load by representing with the resultant concentrated load, and we should know where it's going to act. Now here you can see how I simplified the uniformly distributed load into a resultant concentrated load and how I mark the reaction components. Hope it's clear how this 40 kilonewtons comes. That's by the uniformly distributed load of 40 kilonewtons per meter acting through 1 meter. So 40 kilonewton per meter multiplied by 1 meter ended up with 40 kilonewtons. And the uniformly distributed load is acting through a length of 1 meter. So the resultant force is acting at the center of that length, which is 0.5 meters. Okay, let's calculate the reaction forces for this beam. Now before calculating the reaction forces, it's better to check whether this structure is statically indeterminate or statically determinate. How can we do that? We should check the number of unknowns in this structure, and we should see whether the number of equations are sufficient to find the number of unknowns. As you can see, there are three unknowns in this structure: RA, RB and RY. And how many static equilibrium equations we have? 3, isn't it? So 3 unknown forces, 3 equations, which means we can calculate the reaction forces using these 3 equilibrium equations, which means this structure is statically determinate. So we'll apply the static equilibrium equations to calculate these unknown forces. First, I'll check the horizontal stability of the structure. So this is a horizontally stable structure. So I apply the equation horizontally and get all the forces acting in the horizontal direction and the total load should be equal to 0. Here Ry is a horizontal load acting towards the arrow that I marked in the equation, so which is a positive value. And at C you can find a force component acting horizontally, that is 10 root 2 in 2 times cos 45. It will ended up with 10 kilonewtons. So that is horizontally applied against the arrow that I marked in the equation. So which means it's a minus 10. So those are the only two external loads I can see in this beam. So my equation is Ry minus 10 equals 0. So this should be equal to 0 because this structure is horizontally stable. So there are no uh, resultant force acting in the horizontal direction. So that concludes my Ry value as 10. Now I am going to apply the second equilibrium equation, which is all the total force components act in the vertical direction should be equal to 0. So what are the force components acting vertically in this structure? You can find Ra 40 kilonewton, Rb, and the force component due to the 10 root 2 kilonewton load. Now that vertical force is 10 root 2 times sine 45. So the that force is equal to 10 kilonewtons. Now if I uh, get all these forces into the equation, you can see Ra, that's a positive value because I consider the upwards loads are positive. So Ra minus 40 because 40 is downwards, minus 10 because the 10 kilonewton is downwards, and plus Rb, that is Rb is upwards. Now adding together all these forces for the equilibrium of this structure, it should be equal to 0. Therefore, Ra minus 40 minus 10 plus Rb equals 0. So you can make the equation as Ra plus Rb equals 50. Now I am applying the third equilibrium equation, that is a moment at any point should be equal to 0 because this structure is in equilibrium. So you can see in the equation I am taking the moment at A. It's uh, up to you to decide which point that you are selecting for this uh, moment equation. If you like, you can take the moment at B or anywhere uh, in this beam, but I select to get the moment at A. Then when we consider the moment that affecting when we getting the moment at A are, the first load is 40 kilonewton. The moment created from the 40 kilonewton is 40 kilonewton times 0.5 meters, and the vertical force component of 10 root 2 kilonewton, that is 10 times the length to that vertical force is 1.6 meters. So 10 times 1.6 is the moment. Now those two moments are clockwise because MA I consider clockwise forces, clockwise moments as positive. So the 40 kilonewton, the moments due to 40 kilonewton and 10 kilonewton are positive. Then the last force create the moment is RB for this equation. RB times the length is 2 meters. So 2RB, it's a anti-clockwise moment. So it will be a minus value. To the overall stability, adding all these moment components should be equal to 0, which means 40 times 0.5, 10 times 1.6 minus 2 times RB equals 0, which will end up with RB equals 18 kilonewton. Now using the equations 2 and 3, you can find the value for RA. RA is 32 kilonewtons. Once we calculate the reaction forces, now we can start developing the bending moment, shear force and axial force diagrams. As you know, each diagram represents its respective internal force variation along its length. For an example, bending moment diagram represents the bending moment variation of the beam along its length. So if we can derive some equations to calculate the respective internal force with respect to the length, we'll be able to develop each of these diagrams. To derive these equations, we should consider free body diagrams along the length x where the external loading gets a change. We'll try to identify the external loading gets a change in this beam. Now the external loading variation from A to B, starting from A, we can see a 40 kilonewton per meter uniformly distributed load is applied from A to D, and there are no any other forces, other external forces in between A and D. From D to C, that the uniformly distributed load changes, and that's only is up to, that load is only up to D, and from D to C there is no any load. So the external load changed from at D, where uniformly distributed load comes till D, and then there is no any force from D to C. But at C there is a external load applied at C, and after C again there is no any external load till point B. So basically we can identify three different sections where the external loading gets a change. So what we have to do here is to derive equations for each internal force with respect to the length of the beam. The length is the variable here. So as you can see, I have marked the length as x starting from point A. But if you prefer, you can measure the length from the other end too. But I have selected to start the length variation from point A. Now to obtain equations, we should cut the structure at each section, and we should draw free body diagrams. Then we should treat those as free bodies and should derive equations for the internal forces with respect to x, so that you can find bending moment, shear force, axial force for each section with respect to the length x. So you can see I drew the free body diagram for the first section with the length of x. You can see in the free body diagram I marked the length as x, and I have marked the internal forces, shear force S, bending moment M, and axial force A at the cut section. So what you should remember is the equations that we are deriving here for this free body diagram is only valid from A to D. By considering the stability of this free body, we can apply the three static equilibrium equations to obtain S, M, and A. First, I'll apply the horizontal equilibrium equation. So, as we explained before, so for the horizontal equilibrium, all the force components add together in the horizontal direction should be equal to 0. So here the forces acting in horizontal direction are A and 10 kilonewton. Both the loads are in the same direction, so the equation should be A plus 10 equals 0, because this free body is in equilibrium. So at the end you can get the final answer as A equals minus 10 kilonewton. Now we can apply the second static equilibrium equation for the vertical stability. Now in the free body diagram you can see the uniformly distributed load 40 kilonewton per meter is acting through the length x. Now we have learned in our previous lectures to simplify this uniformly distributed load. We can represent this uniformly distributed load with a resultant force, and we can find where the resultant force acts. So 40 kilonewton per meter into the length of x, you can calculate the total force as 40x, and the length is x, so the load is acting at the midpoint of the total length, because it's a uniformly distributed load. So the length where the distributed the concentrated load apply is x divided by 2 from the point A. So for the vertical stability, we should find what are the forces acting in the vertical direction. For the equation, I consider all the loads upward as positive. So starting from point A, you can see a vertical force of 32 kilonewton upwards acting at A. So and 40x load is acting downwards, and so in the equation you can represent that as minus 40x, and at the end you can find the shear force S again acting downwards, so it's a minus S. So to the vertical equilibrium, adding all these loads should be equal to 0. So my equation is 32 minus 40x minus S equals 0. There you can find the S with respect to x. Now my S is 32 minus 40x. Finally, I can apply the third equilibrium condition, that is a moment at any point should be equal to 0. So I can get the moment at the distance x from A. So my moment equation is m, that is the bending moment, and 32 times x, because the external load 32 times the distance is x, the moment creating at the cut point is 32x, and due to the concentrated load represent where the distributed load, the load is 40x and with the distance of x over 2. So that is that moment applies in the anticlockwise direction. So it should be a minus value. So adding all these moment components should be equal to 0 for the overall stability. So my equation is m plus 32x minus 40x times x over 2 equal to 0. And finally we can end up with the equation for m equals 20x squared minus 32x. So when we getting the moment, we should get the moment at the point where we made the cut. So we can avoid the shear force component acting in the moment equation. So that's why I got the moment at the place where we cut the structure. So you can see now we have derived three equations for the axial force, shear force and bending moment respectively. So these three equations are valid, as I said before, only from A to D of the beam. So these equations are represent the internal force variation between A and D. Right. Now we can draw the second free body diagram where we cut the structure in between D and C of the beam. Again, in this free body diagram, you can see the uniformly distributed load of 40 kN per meter acting through a length of 1 meter. Now you know how to represent this 40 kN per meter uniformly distributed load with a representative concentrated load, like this way. Now you can see in the figure I have represented the 40 kN per meter uniformly distributed load with a representative 40 kilonewton, that is the equivalent force. You know how to calculate the equivalent force there, because our 40 kilonewton per meter is acting through a 1 meter length. So multiplied 14 by 1, you will get 40 kilonewton, and it is acting at the center of this uniformly distributed load, where 0.5 meters from point A. Once we draw the free body diagram, we know what are the steps we need to follow to get the equations for S, M and A. Like we did before, we should apply the three static equilibrium equations for the overall stability of this free body. So for the horizontal equilibrium of this free body, we can apply the horizontal equilibrium equation. So as in the previous section, 10 kilonewton meters in the direction of in horizontal direction, and also axial force A is in the same direction. So A plus 10 equals to 0. Then we can get the value for the axial force A as minus 10, and the vertical equilibrium of the of this free body, we can get the equation as 32 minus 40 minus S equals 0. There we can get the value for S, which is equals to minus 8, and the moment at the point where we cut the structure. So we get the moment from there as we did before. We consider clockwise as positive. So M and 32 times X and 40 times the length to the load 40. Now what is the length to the load 40 from the point where we cut the structure? So the total length we consider as X, and the load acting from point A is 0.5 meters. So you can get the distance as X minus 0.5 is the distance from the cut end to the 40 kilonewton load. So the equation is M plus 32 times X minus 40 X minus 0.5. That the total moment should be equal to 0. By solving this equation, we can get the answer for M. M is 8x minus 20. So now these three equations we derived, for which is applicable only from the section D to C. Right. Now I think you know how to cut the next section and draw the free body diagram. As you can see in the picture, I have made the third free body diagram where I cut my structure in between C and B. Similarly, you can see I have represented the 40 kilonewton per meter uniformly distributed load as a concentrated load. So we should apply the three equilibrium equations as we did in the previous two cases, and we should find the values for shear force, bending moment, and axial force. First, as I did before, apply consider the horizontal equilibrium. So all the force components in the horizontal direction adding together should be equal to 0. There you can get the value for A. Now in this case, you can see what are the forces acting in horizontal direction. A, and that is axial force, and the 10 kilonewton still there, plus now the force component from the 10 root 2. The force component, the horizontal force component is included in this equation, at the end we can get the answer as 0 for the axial force. And for the vertical equilibrium, you can apply the you can get the vertical force components, and that should be equal to 0. So I don't need to repeat how we did this thing for this section. Similar way we have to follow that to get this equation, and we can get the answer as S equals minus 18. And lastly we apply the moment, the overall moment at any point should be equal to 0 for the overall stability. So I'll get the moment at the point where we cut the structure. There you can see that 40 kilonewton acts in the distance of x minus 0.4. Now you know how to get that. And also the vertical load due to the 10 root 2 force, which is acting in the distance of x minus 1.6. Hope you can understand how we get that distance. So by solving this equation, we can get the moment as 18x minus 36. So these are the three equations we derive to represent the axial force, shear force, and bending moment. Remember, as I said before, these three equations are only applicable in between C and B of this beam. You may wondering why I select the left hand side portion of the cut section for all the time to calculate the axial force, shear force, and bending moment. You may wondering whether why we can't take the right hand side. Of course we can take it. I mean, in this section you can see the left hand side there are so many forces, 32 kilonewton, starting from 32 kilonewton till the cut section, the point where we cut the structure, there are so many external loads. But if we consider the right hand side, it's only 18 kilonewton load acting at the point B. So when we selecting the section, we should be very careful, because we don't need to complicate our calculation. If you find an easy way to get the answer, you can of course do that. So here we'll check if we take the right hand component of the structure, whether we'll get the same answers. Here I draw the free body diagrams for the left hand side and right hand side. Now in the box, the colored box, you can see the equations that we derived from the left hand side component, and we'll derive the equations for the S, M and A using the equilibrium of the right hand side too, and see whether we'll get the same answer. For the horizontal equilibrium, if we apply uh, if we calculate all the loads in the horizontal direction, you can see A equals 0. Now in the left hand side section, we get the same answer. And for the vertical equilibrium, for the right hand side free body, 18 plus s equals 0. Then s equals minus 18. If you check the left hand side answer, it's the same. And if you get the moment, you can check the moment equation, m in the clockwise direction, and the only force in the right hand side is 18. Now the length or the distance, we should be careful. We have started measuring the length from point A. So the, the x value equals 0 at point A, and x varies from point A to B. So which means the distance between the cut section to the point B is 2 minus x, because the total length is 2 meters of this beam, and the the length to the cut section should be 2 minus x, and using that we can get the moment equation. And after solving the equation, we could find m equals 18x minus 36, same as the left hand side equation. So if you feel like considering the right hand side is an easy way of calculating this, no problem, you can use it. But you may have noticed that the notation of the bending moment, shear force, and axial forces is the marking would be different from left to right side. That's because following the sign convention. For the axial forces, we say tensile force is a positive one. So from B, I applied the tensile force, as you can see in the figure. Similarly, the bending moment, hogging moment is positive, and shear force clockwise positive. So if you apply the sign convention correctly in the left hand side or right hand side, and if you measure the lengths correctly to both sides, you will get the same answer. So it's completely up to you to decide which uh, part of the beam that you are considering for draw the free body diagram. Okay, now we have done all the calculation part, and it's time to draw each diagram. First, we will start with the axial force diagram. So I just included all the equations that we got it from the respective sections. You can see in the red boxes. From A to D, hope you can remember, we got the equation for axial force is A equals minus 10, and from D to C again A equals minus 10, and hope you can remember in the last section analysis we got it A equals 0 from C to B. Now we can draw uh, the axial force diagram. A to D, it's minus 10 kilonewton, right? So you can mark the 10 kilonewton line, and from D to C again minus 10 kilonewton. I'll just mark that too in the diagram, and C to B, it's 0. So now that is the end of drawing the axial force diagram. So you should mark the values in the respective places to completeness of this axial force diagram. Okay, let's draw the shear force diagram too. You can see in the red boxes that I have marked all the shear force equations we got from the three free body diagram analysis. In the first section, from A to D, we got the shear force equation as S equals 32 minus 40x, and hope you can remember these equations. And from D to C, we got it S equals minus 8, and in the last analysis of the free body in between section C and B, we got S equals minus 18. Right, now it's just a matter of drawing these the diagram using these equations. Now you can remember the x value. We started from measuring x at point A, which means when x equals 0, it should be point A, and when x equals 2 meters, it will be point B. So to start drawing the diagram from A to D, we can apply x equals 0 to the equation, and we can find the first the starting point of the diagram. So s equals 32 minus 40x. When the x equals 0, that equation becomes s equals 32. So we can mark the 32 kilonewton in the diagram. And the next point is the end point of this section A to D, which is at 1 meter. Until at 1 meter, we can apply the equation s equals 32 minus 40x. So at 1 meter, the value for s is 32 minus 40 times 1. So the answer for the shear force at 1 meter length is 32 minus 40, which means minus 8. Now when we drawing the this diagram, you can see s equals 32 minus 40x. It's like y equals mx plus c type equation. So m is minus 40 here, and c is 32. So likewise you can think in that way and draw the diagram. So we'll draw from 32 kilonewton to minus 8, and you can double check your answer with that y equals ms plus c type equation diagram, and it's ended up at 1 meter with the value of 8 kilonewton. Right, from D to C, it's a constant value, s equals minus 8. So you can draw s equals minus 8 from D to C. And from C to B, it's again a constant value of minus 18. You can draw that minus 18. You can mark the minus 18, and you can draw the diagram. Right, now this is the shear force diagram for the beam AB. Okay, now the last one, bending moment diagram. As I mentioned before, I have included the three equations we derived from the three free body diagram analysis in the red boxes. So from A to D, the applicable equation is m equals 20 times x squared minus 32x. And from D to C, m equals 8x minus 20. And from C to B, m equals 18x minus 36. Now, as I said before, x varies from 0 to 2 from point A to B. So, the starting point of this diagram, we can apply x equals 0 for the moment m equals 20x squared minus 32x. When we apply x equals 0, then m is 0. So starting with 0, then we should proceed with drawing the diagram. From A to D, we should draw the diagram by using the equation m equals 20x squared minus 32. So we know the starting point value is 0 and end point value you can get it from applying x equals 1, because this equation is valid till point D. So the end point is D, which is x equals 1 meter. So if you plug the value x equals 1 in the equation, m equals 20 times 1 squared minus 32 times 1. Basically, m equals 20 minus 32. The answer is minus 12. So starting point is 0, end point is minus 12, and you can draw the curve matching to this equation. Hope you know how to draw this kind of a curve with match with the equation. So I'll draw that curve now, and as I said, end point is minus 12 kilonewton, and you can find the maximum value as well by using the integration. So once we integrate this equation, you can find the x value where the maximum occurs. So you get the x value as 0.8 meters, then you apply x equals 0.8 into this equation, you can get the maximum value. So that is minus 12.8 kilonewton meter. From D to C, the equation is m equals 8x minus 20. So again, it's like y equals mx plus c type equation. So similarly, you can plug the values to x and get the starting point at the end point. So the starting point when x equals 1, m equals 8 times 1 minus 20, basically 8 minus 20 equals to minus 12. So which means the starting point of the section DC of the diagram is equal to the end point of the diagram of AD. So now we know the starting point as minus 12 kilonewton meter, and end point we can apply x equals 1.6 meters to the equation. So m equals x times 1.6 minus 20. So it will be the value 7.2 kilonewton meters minus. So we can draw the diagram in between D and C like this. Ended up with minus 7.2 kilonewton meters. And from C to B, the equation is m equals 18x minus 36. So the starting point, we can apply x equals 1.6 and get the value. So when x equals 1.6, my m value is 18 times 1.6 minus 36. So when you do the calculation, you will get it m as minus 7.2 kilonewton meter. So as in the previous case, starting point of the value and the end point of the section DC is the same, and the end point of the section CB when x equals 2, you can get the value. Apply m equals 18 times 2 minus 36. You can get the value, that is 0. Then you can draw the diagram like this. Right, this is the bending moment diagram. I hope it's clear to you how to draw the axial force diagram, shear force diagram, and bending moment diagram. Now the question asked was to draw these three diagrams. Now we have done the part and draw the three diagrams. In addition to that, I'd like to brief you about some relationships between load intensity, shear force, and bending moment. The first relationship is between the load intensity and the slope of the shear diagram. So the slope of the shear diagram, that is ds over dx, is equal to the load per unit length or the distributed load intensity of the applied load. So it's clear that the load intensity in between AD is 40 kilonewtons per meter. So my slope, the shear force diagram slope, is also 40. So that is the first relationship. Secondly, uh, you can find that S equals dm over dx, which means the shear force at any point along the beam is equal to the rate of change of the bending moment, or in other words, the slope of the bending moment. So you can find the shear force at any point along the beam by getting the slope of the bending moment diagram. If you check the two diagrams, you may find that relationship between the two diagrams. Thirdly, we can show that the bending moment M is maximum or minimum whenever the shear force S is 0. So you can see in the diagram, I just draw the blue line. So the shear force is 0 when the bending moment is maximum in the bending moment diagram. Finally, we should know if the Fx, the load intensity, is 0, then shear force is a constant, m is a linear function of x. Also, when Fx is a constant, shear force is a linear function of x, and bending moment is a quadratic function of x. You can see those relationships by looking at the bending moment, shear force diagrams, and the load intensity of the beam. So with that, we'll conclude this video. Hope you understand about how to draw the bending moment diagram, shear force diagram, and axial force diagram in this method. Thank you.